Hello, I'm Kwanjong Park, PhD student from Songyungan University, and today I'm presenting our work titled Carbon-Aware Continuous Learning for Sustainable Real-Time Machine Learning Analytics. The goal of this research is to make continuous learning systems which support real-time machine learning analytics more sustainable by integrating carbon awareness. Machine learning models are widely employed to perform real-time ML analytics on video and audio data generated across various applications such as driving scene understanding, traffic monitoring, and automatic speech recognition. These ML models are often deployed on on-premise edge servers due to two key advantages. First, edge servers are typically located near the application's data sources, thereby reducing network latency by processing data locally. Second, they enhance data privacy by keeping sensitive information within the local network instead of sending it to third-party cloud services. To process video frames or audio segments in real time, it is common to use compressed ML models. However, their reduced parameter counts limit their generalization capacity. For example, when the data distribution changes or new data patterns emerge over time, referred to as data drift, analytics models are prone to accuracy degradation. To address this problem, continuous learning periodically generates data labels with a large teacher model and retrains a lightweight student model using these labels. This allows the system to adapt quickly and preserve accuracy over time. However, this labeling and retraining process is highly compute intensive. It requires about 3.3 to 9 times more computing resources than performing only inference. These increased computational demands result in higher energy consumption of edge servers. Our experimental analysis showed that over a 12-hour run with a ResNet 152, ResNet 18 teacher-student model pair on a single RTX 3019 GPU for a driving scene understanding task, continuous learning consumed 26.4 times more active energy than inference-only execution for achieving a 24.3 percentage point accuracy gain. This highlights the trade-off between accuracy improvement and energy cost incurred by continuous learning. Additionally, since most globally distributed edge servers rely on carbon-emitting energy sources, a rise in energy usage directly amplifies their carbon footprint. This in turn raises critical concerns about sustainability and climate change mitigation. To illustrate, 375,000 edge servers supporting urban autonomous driving in the USA generate a carbon footprint of approximately 4.99 times 10 to the 8th kilograms CO2 equivalent when performing video analysis with continuous learning. This carbon footprint is equivalent to annual emissions produced by these. In fact, the carbon footprint of continuous learning depends not only on how much energy is consumed, but also on the carbon intensity of the power grid, that is, how much greenhouse gas is emitted per unit of electricity generated. As shown in the figure, carbon intensity fluctuates significantly over time. Retraining during high carbon intensity periods results in much higher emissions, whereas performing the same task during cleaner, low carbon periods results in a smaller carbon footprint. As a result, adapting to fluctuations in carbon intensity is crucial for minimizing carbon footprint of continuous learning. Previous studies on continuous learning systems can be broadly categorized into two groups, those that focus on resource efficiency and those that target power efficiency. However, despite these advancements, existing CR systems overlook carbon intensity, thereby failing to optimize the system's carbon footprint. Outside the scope of CR systems, several studies have been conducted to reduce the carbon footprint of cloud and on-premise data centers. These studies have largely proposed general carbon-aware low workload scheduling strategies by deferring computations to time periods or geographic regions with lower carbon intensity. However, these schemes cannot apply to CR systems because they neglect continuous learning specific parameters. In CR systems, timely model retraining in response to data drift often conflicts with the goal of scheduling retraining jobs during periods of low carbon intensity. For example, deferring retraining to periods and renewable energy is redundant, can improve sustainability but risks accuracy degradation due to prolonged model staleness. Consequently, addressing the aforementioned conflicts requires a fundamental reconsideration of when and how real-time ML analytics models are retrained on edge servers to incorporate carbon awareness into the continuous learning system. To this end, our approach combines temporal shifting with application level adaptations to jointly reconfigure the timing and intensity of continuous learning operations. We demonstrate that such a coordination unlocks opportunities for achieving the goal even in the presence of irregular, unpredictable data drift and fluctuating carbon intensity. We identify three key components that serve as control nodes in this reconfiguration. The first node is teacher model selection for labeling. Teacher models with higher generalization capability, such as WildLegionNet 101 or Swing Transformer Base, tend to increase more carbon emissions but produce more accurate labels, which in turn enables the student model to learn from less noisy gradient signals. The second knob is the decision on the timing of retraining. The retraining threshold specifies the accuracy level that triggers retraining. Setting a higher retraining threshold makes the system more reactive to accuracy drops and enables faster adaptation to data drift, but it also results in more frequent retraining, thereby increasing carbon emissions. The third knob is the decision on the extent of retraining. Intensifying retraining by increasing the training data size or the number of epochs yields diminishing improvements in accuracy due to the law of diminishing returns, while carbon emissions increase almost linearly. Although each configuration component exhibits distinct characteristics, jointly reconfiguring them offers greater opportunities to reduce carbon emissions while preserving acceptable accuracy. Like this, the graph shows the potential impact of joint reconfiguration of both accuracy and carbon footprint. The x-axis represents values normalized to the carbon footprint of a method without using continuous learning, and the y-axis indicates the final accuracy across the entire workload, with the better policy appearing toward the upper left corner. The energy optimal policy results in a higher carbon footprint than the carbon footprint optimal because it did not account for temporal fluctuations in carbon intensity. Compared to the oracle, the accuracy optimal policy achieves higher accuracy, but at the cost of much higher carbon emissions, while the carbon optimal policy saves carbon but sacrifices accuracy. This finding underscores opportunities for designing a carbon-aware CL scheme. However, fully leveraging joint reconfiguration in CL systems requires overcoming two challenges. The first challenge comes from a massive and dynamic configuration space. We need to jointly decide among enormous number of combinations that are practically untenable. On top of that, the environment is non-stationary. The second challenge arises when multiple labeling models are employed. Since each teacher may produce different labels or confidence scores for the same input sample, it becomes unclear whether the student model actually improves after training or if the observed change simply comes from using a different teacher model. From the outset, relying on teacher models for every evaluation is both unreliable and unsustainable, thereby requiring a lightweight surrogate evaluation mechanism that can estimate the expected accuracy carbon trade-offs. We propose a carbon-aware continuous learning system for sustainable real-time ML analytics called CCL with the primary objective of minimizing carbon footprint while preserving model accuracy. CCL is composed of three main components: CCL agent, worker, and repository. The CCL agent is responsible for jointly reconfiguring the three control components. It continuously monitors real-time signals to determine when and how to reconfigure. To make these decisions efficiently, it uses reinforcement learning approach, which enables online exploration without exhaustive profiling. The worker operates on edge server accelerators. These operate separately from the accelerator used for real-time ML analytics. It performs labeling with the currently selected teacher model and retrains the student model using the configuration chosen by the CCL agent. The repository serves as the memory system. It stores metadata such as carbon intensity traces, teacher models, and class distribution statistics, and performance history from past retraining sessions. CCL defines a utility function that quantifies the trade-off between accuracy and carbon footprint for each configuration of the CL process. This function is conceptually simple. It measures how much accuracy we gain normalized by how much carbon we spend. Higher values indicate better configurations that achieve higher accuracy with lower carbon cost. To make this more practical, we decompose this into three contributing components: lambda, gamma, and omega. We then combine these components into a single weighted summation form where alpha controls the balance between accuracy and carbon efficiency. A larger alpha means the system emphasizes accuracy, while a smaller alpha means it prioritizes sustainability by reducing carbon emissions. For a more detailed the rationale and derivation behind this formulation, please refer to our paper. The goal of this agent is to find the optimal jointly configuration policy, denoted as phi star. Specifically, it aims to maximize the cumulative utility function over the entire deployment period T by jointly deciding three configuration nodes. However, the total action space becomes extremely large, so directly exploring this huge space is computationally infeasible for online learning. To make this problem tractable, CCL prunes the search space through three key steps as shown on the right. First, we perform labeling model pruning. Second, we apply retraining threshold discretization. Third, we compress the retraining hyperparameters. After these pruning steps, the action space is reduced in that way, enabling tractable joint reconfiguration in real time. Finally, we model this process as a Markov decision process and optimize it using PPO, like this. Let's follow our algorithm of carbon-aware joint reconfiguration policy. When an ML application is registered on the target system, it starts with the initialization phase, which initializes necessary variables and pruning unpromising configurations. It then proceeds to the runtime phase to jointly reconfigure the three nodes over the deployment period. Now we move on to the runtime phase. Constructing a joint reconfiguration policy naturally involves two key behaviors: exploration and exploitation. As shown from lines 8 to 11, the CCL agent automatically and efficiently explores the target action space. To do this, we use an uncertainty-aware strategy called VDBE softmax. The idea is simple. The agent looks at how much the estimated Q value differs from the actual Q value observed before and after reconfiguration. At each step, the action first observes the current state, then generates a random number between 0 to 1. If the number is smaller than epsilon t, the agent explores, selecting an action probabilistically using softmax over the current Q values. Otherwise, it exploits, choosing the action with the highest Q value. Once an action is selected, the agent executes it by updating the corresponding configuration. After that, the system computes the reward based on the utility function and updates the exploration threshold. Now, one more consideration in continuous learning is that one-time tuned reconfiguration policy can become obsolete. To solve this, CCL agent continuously refines its policy during runtime to maintain the optimal trade-off between accuracy and carbon cost. It does this by leveraging recent records of states, actions, and rewards that it collects through real-time interaction with the environment. All of this information is stored in a repository. Then CCL agent triggers a policy refinement whether the average reward is below the repository's mean, or when the reward variance becomes unusually high. Therefore, as time progresses, CCL agent eventually transitions to a deterministic decision-making process once the reconfiguration policy has sufficiently converged on the fly. However, when confronted with environmental changes, epsilon increases, reading the policy to explore new states in order to recalibrate the control nodes. This guided exploration reduces the likelihood of selecting empirically inferior CL components during the runtime phase. Furthermore, CCL agent incorporates exploration outcomes into policy refinement, thereby improving the adaptiveness of its policy to variations in the CL environment and optimizing for the objective equation. The experiments were conducted on an edge server grade RTX 3019 GPU, and other experimental setups are as follows. We evaluated CCL on three representative real-time ML analytics applications: driving scene understanding, traffic monitoring, and automatic speech recognition. For automatic speech recognition, we converted each audio clip into a log-mail spectrogram as input for the CL pipeline. We used real-world carbon intensity traces from 5 different geographical regions. These traces, obtained from electricity grid operators or public datasets, represent the time-varying carbon intensity of power grid that can supply the edge server. All traces span the same time period, ensuring the consistent basis for comparison. The selected regions span a spectrum of grid profiles as illustrated in this figure. This variety allows us to evaluate how CCL performs under different environmental dynamics. In our evaluation, we compared CCL's policy against both 4 theoretically optimal baselines and 3 non-objective baselines. The details are shown in this table. Now let's look at the overall accuracy carbon footprint analysis shown in this figure. Each plot corresponding to one application, and the x-axis represents the carbon footprint normalized by CF optimal, and the y-axis represents the final aggregated accuracy. We can see that CCL, shown in blue, consistently achieves a superior balance between accuracy and carbon footprint across all 3 workloads. It approaches the performance of the Oracle policy, which assumes perfect knowledge of data and carbon conditions, but does so without any prior information, only through online learning and runtime adaptation. Overall, CCL's Pareto curve consistently dominates all non-Oracle baselines. Next, we analyze how CCL maintains accuracy over time under continuously changing runtime conditions. As you can see, CCL's accuracy curve closely follows that of Oracle throughout the entire runtime. Across all 3 workloads, CCL achieves final accuracies within 1.8 to 2.5 percentage points of Oracle, while maintaining a carbon footprint. This demonstrates that CCL effectively learns to adapt to data drift and carbon fluctuations in real time, achieving a near-optimal carbon accuracy balance. And importantly, it does so without any prior knowledge or offline profiling. To understand how CCL achieves the performance improvements shown earlier, we analyzed its internal behavior using the driving scene understanding workload as a case study. This figure shows how CCL jointly reconfigures its 3 control nodes across 4 3-hour periods. Starting from the top, the pie charts show the ratio of teacher models used in each period. The middle plots show retraining frequency and configuration selections, and at the bottom you can see the carbon intensity trace for each time window. This dynamic adaptation demonstrates how CCL effectively balances accuracy and carbon in real time, adapting both how it runs and from when it runs based on the current environmental and workload conditions. We next analyze the runtime overhead of CCL. As you can see in the upper pie charts, the CCL agent's operations and policy self-refinement occupy only a tiny fraction of the total computation, less than 2% of overall computation. This means that the reinforcement learning-based control logic introduces low computational burden. To validate our design choices, we performed evaluation studies on the driving scene understanding application by selectively removing each of CCL's 3 core components. The results show that its design components, pruning, uncertainty-aware exploration, policy self-refinement,
is essential for CCL's design. This figure shows how the three reinforcement learning hyperparameters influence the performance of CCL in the driving scene understanding application. Overall, finding the right combinations of eta, tau, and sigma is key to stabilizing and optimizing CCL's reconfiguration policy. We applied these tuned hyperparameter values in our main experiment, as shown earlier in the overall performance figure, and consistently achieves superior accuracy carbon balance across all three applications. This figure shows how CCL performs under different regional carbon intensity traces. Overall, CCL maintains robust and consistent performance across all regions, closely tracking Oracle's performance in both accuracy and carbon footprint. You can see that the differences are smallest under the Great Britian trace, which shows the most stable carbon intensity. In contrast, regions like South Australia and New York, where carbon intensity fluctuates significantly over time, show greater relative reductions in carbon footprint, which demonstrates that CCL adapts more aggressively when the environment is dynamic. From a broader sustainability perspective, as regional power grids continue to decarbonize, the absolute savings from carbon-aware scheduling will naturally decrease. However, the relative efficiency gains can actually grow larger because cleaner grids amplify the difference between high and low carbon periods. So even as renewables increase operational carbon reduction, through adaptive systems like CCL remains highly relevant and impactful. So far, our discussion has mainly focused on operational carbon footprint, that is, the emissions that can be directly reduced through software-level mechanisms such as scheduling or reconfiguration. However, another important component is that the embodied carbon footprint, which represents the fixed emissions generated during the manufacturing and deployment of hardware such as GPUs, storage, and networking devices. As hardware becomes increasingly complex and energy efficiency continues to improve, it becomes essential to evaluate both operational and embodied emissions together, since only their combination truly represents the total life cycle carbon footprint of ML systems. The graph shows the CCL's 4-year total carbon footprint reductions normalized by accuracy optimal across 5 regions with embodied carbon stacked at the bottom. As we can see, the total life cycle reductions achieved by CCL reach from 40% to 78% under 5 traces across 3 workflows. These results highlight that even when we include embodied emissions, the operational carbon savings achieved by CCL remain substantial and impactful. In conclusion, we show that jointly reconfiguring the labeling model, retraining threshold, and retraining hyperparameters significantly reduces the carbon footprint while maintaining accuracy in CR systems, albeit with its own challenges. To this end, we propose CCL, a novel carbon-aware CR scheme that automatically balances the trade-off between accuracy and operational carbon footprint through an reinforcement learning-based joint reconfiguration policy. We validate the effectiveness of CCL through comprehensive experimental evaluations with using carbon intensity traces from 5 regions and 3 real-time ML analytics applications.